Kinematics memo number 1. Define the following terms. Distance, total length covered irrespective of the direction of motion. Displacement, direct distance moved in a certain direction from start to end point. Speed, the distance travelled per unit time. Velocity, the rate of change of displacement. Acceleration, the rate of change of velocity. B. What does the gradient of a displacement time graph represent? Well, it's the instantaneous velocity. What does the gradient of a velocity time graph represent? Well, it's the instantaneous acceleration. What does the area below a velocity time graph represent? It is displacement. Number 2. A vehicle is moving at a constant velocity of 20 meters per second. The brakes are applied as the vehicle is approaching traffic lights and decelerates at 2 meters per second squared. Find the time taken for the vehicle to come to a standstill. Well, we're going to use v equals u plus at and rearrange that equation to make t the subject. 20 divided by 2 is 10 seconds. B. Find the displacement travelled from the time the brakes are applied to when the vehicle stops. Well, now we're going to use v squared equals u squared plus 2as, rearranging to make s the subject. So minus 20 squared divided by brackets 2 times minus 2, and we get 100 meters. Number 3. A stone falls from a cliff 25 meters high. Given that the stone was originally at rest, find A. the time taken for the stone to fall. Well, now we're going to use s equals ut plus a half at squared. So 25 is equal to, well, as it started from rest, 0 times t plus a half times 9.81 times t squared. And we get an answer of t equals 2.26 seconds. The final speed as the stone hits the ground, well, now that we know the time it takes to drop, we're going to use v equals u plus at. So that's 0 plus 9.81 times by 2.26 seconds, and we get 22.2 meters per second. Number 4. A football is kicked with a velocity of 15 meters per second at an angle of 35 degrees to the horizontal across the field. A. Find the horizontal component of the velocity. Well, this is going to be using cos, so 15 cos 35 is 12.3 meters per second. Find the initial vertical component of the velocity. Well, that's 15 times sine 35, and that's 8.60 meters per second. Find the time for the ball to reach the highest point. Well, the highest point is going to be going vertically. It's going to have no velocity in the vertical. So v equals u plus at. 0 equals 8.6 plus minus 9.81 times by t. Rearranging to make t the subject, we get 0.88 seconds. D. Find the total horizontal displacement the ball goes through until it lands. While the total distance travelled in the horizontal is, well, also the total time, travelled is 0.88 times by 2, because it's going to go up to the highest point and back down again to the same level. And using the unrounded answer, we get 1.75 seconds. Distance is speed times by time, so 1.75 times 12.3, we get 21.6 meters. 5. A ball is kicked horizontally with a speed of 5 meters per second off a bridge that's 30 meters high. Assume air resistance to be negligible, so we can use the equations of motion. A. Find the time for the ball to hit the ground. Well, s equals ut plus a half at squared. So 30, and again, because it's starting from rest, is in the vertical. We've got 0 times t plus a half times 9.81 times t squared, and we find that t is 2.47 seconds. Find the distance from the base of the bridge to where the ball lands. Well, again, we're going to use speed times by time is distance. So 5 times 2.47, we get 12.3 meters. C. Find the magnitude of the displacement from the top of the bridge to the point where the ball hits the ground. Well, we're going to just use, as we only need to know the magnitude, we can use Pythagoras. So a squared plus b squared equals c squared. So 12.3 squared plus 30 squared is c squared, which is 1052. Rooting that, we get c is 32.4 meters. Finally, number 6. Satellites in orbit follow a circular path. What is the angle between the velocity and acceleration vectors in order for them to follow this path? Well, they have to be continuously at a 90-degree angle.